So today we're going to start speaking about the ventilation loads. We will speak about this next week as well, because it's not difficult, but those are new concepts. We haven't talked about this yet in building science. So in building science, basically we have two kinds of thermal loads. The loads going through the envelope of the building, we are done with the envelope. We have calculated loads through the roof, the walls, windows, floor, basement. So we are done with it. And now we are going to work with ventilation loads. So the first tool that we have to know is this psychrometric chart. Okay, so you have this word, probably it is the first time you have heard of this word, psychrometric. What is this? A good question. I'm sure this is that comes from Greek psychro. I have to find out what it means. And metric means that we can measure something. So that measures the moisture, the temperature and moisture conditions in the air. Okay, so both things are important to assess comfort. Okay, so there are two factors that affect comfort. The first one is temperature. And the second one is humidity. Okay, so we have to control temperature and we have to control humidity. Temperature, we are used to dealing with temperature. Everybody knows what temperature is. And if we are cold, okay, so I need to increase the temperature. I turn on the heating system and that's it. But humidity, it's something that, well, we can't see temperature. It's something that we don't see. We feel temperature. The problem with the humidity is that we don't see humidity. Well, we can see water, we can see the rain. If it rains, we see that it's raining, or we can see the snow if it's snowing, and we can see a river if there's a river. So we can see water, but humidity, it's related with moisture and vapor and water vapor. Okay, so when we are talking about humidity, we are talking about vapor, we are talking about liquid, and we are talking about solid, water, ice. Okay, so for sure we can see water, actual water, and we can see ice, but we don't see vapor. We notice, especially when there is too much, or when there is too much, we notice this. If there are like 50 people or 100 people in a room for 3 or 4 hours, and if and this room is not ventilated, I'm sure that you have opened the door and you say, it smells like stuffy, or what's this? Okay, this is the effect of the vapor of water. Okay, we don't see that, but we feel it. We feel it because it's not pleasant, it's not comfortable. The problem is that we don't see that, and we only feel it because people inside the room, they don't feel that the air is not healthy. You notice it when you enter the room. If you enter from a healthy space to that saturated space, you feel that, okay, this is not acceptable. But if you are there and you are breathing that unhealthy air, you don't notice that you are breathing something that it's not healthy. So that's the issue. Okay. So this is the vapor. We don't see that. We feel it. That we feel we are more sensitive to temperature than to humidity. So we have to control that. And how we control that? By ventilating that. And this tool, this psychrometric chart, relates temperature and humidity. Okay, so we will explain this further in systems, in building systems, the course that you will be taking by this time next year. That this tool relates temperature and humidity. So here we have this chart okay? So these lines or this scale we have here is the dry bulb temperature in Fahrenheit, and we have a dry bulb and wet bulb temperature. We will explain all these concepts again, but dry bulb temperature is the temperature that we measure with a thermometer. Okay, so it's the temperature of the air when it is not saturated with moisture. So we can have a certain amount of moisture in the air, and if this amount of moisture is not 100%, this is the dry bulb temperature. Okay, so dry bulb temperature, comfort temperature, I told you before that it's between 68 and 70 Fahrenheit. Okay, so the comfort, this is 60, so this is 65, that's 68. So I'm highlighting this. No, sorry, this is 65, this is 70, so 68 is here. So between 68 and 74, it's comfort. Okay, so here you see that maybe it's too small. Okay, there you go. So this is 40, 50, 60, 70. So this line is about 68 Fahrenheit. This line is 74. So within these two lines, we are comfortable when it comes to temperature. But then we have another magnitude, which is the relative humidity. Relative humidity, it's a complicated concept. Anyway, the relative humidity is the amount of moisture that we have in the air. Okay, so this is this is the relative humidity. So relative humidity in this chart, you see those lines, those curved lines, and here we have 10%, 20%, 30, 40, 50. 60, 70, okay? So we are in comfort conditions, let's say between 40 and say 55. Yeah, something like that. Okay, so you can see that this line is 40 because this is the 40%. This is 50 and this is 60. So this line here in the middle, it's around 55. Okay, so in that I'm going to make it better. Okay, so this is the rectangle in which we have comfort. So we can have a lot of combinations between temperature and relative humidity. So only in this small rectangle, we feel comfort. Human beings, I mean, other beings, I don't know, but human beings, we are comfortable under these conditions. Okay, so our goal, if we are designing buildings, our goal is to keep indoor temperature within this comfort range, within 68 to 74 Fahrenheit, and between 40 and 55 relative humidity. So that's it. This is what we have to understand today. So if we have a lot of people are breathing and we sweat. So we are, so when we are doing this, we are increasing the relative humidity. So we have a lot of people in a room breathing, just breathing, or if we are in a gym, we are sweating a lot, so we are increasing the relative humidity of the building. But just by breathing, we are increasing the relative humidity. So if we don't ventilate, the relative humidity will grow, and then we will be out of this comfort condition. So we might keep the temperature conditions within the comfort range. That's good. But if we increase the relative humidity, we are not in the comfort range. So we need ventilation. So that's it. The problem is that we ventilate, we are introducing fresh air. If it's cold outside, if our outdoor air it's at 20 Fahrenheit, then we have to heat up this. So we are reducing the amount of water, but we have to heat up that air. Okay, so basically that's we have to deal with these two magnitudes, the temperature and relative humidity. We have this tool, this chart, to measure conditions. If we are calculating the thermal loads, if we are designing a mechanical system, and our conditions, we measure conditions in our building, and those conditions are within these 4 points, it's good. If we are out of these 4 points, then something is not working in our mechanical systems, and then we have to, well, it's a mess. Changing mechanical systems, it's something very complicated. Okay, so this is what we have to understand today about this psychrometric chart. Next week, we will define all these concepts, the dry bulb temperature, the wet bulb, the dew point, relative humidity, humidity ratio, specific volume, and enthalpy. Okay, so all these concepts, we need to become familiar with all these concepts because everything is here. So sometimes we understand temperature, especially the dry bulb temperature. I think we all can understand relative humidity because if it's too high, we feel that there's something wrong there. And if it's too low, relative humidity, if it's below this 40%, we feel that when we are breathing, our throat suffers. It's like we have the dry throat. So we need to increase the relative humidity. Okay, so it's something that we can feel if we are not within these two comfort parameters, 40% and 55. But next week we will define all these magnitudes, and we will speak more about this psychrometric chart. Today, well, we have to, I'm going to explain now what can we do with the relative humidity. What can we do with ventilation? Yeah, so that's the idea. So our goal is to keep people comfortable. Okay, so we are working for our clients. Our clients are our people usually, and we have to make sure that they are feeling comfort when they are using our building. So they might be doing anything, no matter what kind of activity we are developing in our building. But we have the envelope, so we know that envelope matters, especially to keep the temperature at comfort conditions without spending a lot of energy. I have drawn here a bathroom with a toilet because this is how things usually work, especially in houses, in residential buildings or in single family houses, okay? So we have the envelope, we have windows, we have thermal insulation in the wall, thermal insulation in the roof. So there's thermal insulation around the envelope of that building. Okay, and now we have to work with fresh air. So it's very easy because we have fresh air outside, and the fresh air goes through the building. People are breathing, So we increase the relative humidity of this air, and then we have to get rid of it. And the most common place to get rid of this air is through toilets or through kitchens. So in the kitchen, if you are cooking, you know that we have the extractor. So if there's a lot of smoke because we are cooking, we just press that button, and so that means that we are getting rid of this air that is not healthy. And in toilets, we have this, even if we don't notice, but there's like a ventilator or there's like a fan here, yeah, and this fan moves the air. Okay, so this is the ventilation, and on that ventilation, we have the concept of CFM. Okay, what does CFM stand for? It's a cubic feet per minute, and it depends on the number of people. Okay, so I'm going to explain that now, but we have to understand that we need a ventilation. The ventilation, the way or the units that we use to measure the ventilation is CFM, cubic feet per minute. So it's a unit of volume and a unit of time. It depends on the number of people. The more people in the room, the more ventilation, the more amount of fresh air we need. And finally, we have to get rid of this air. Okay. We can open a window. Yeah. Usually we have extraction. So we can do this with we can accomplish this with natural ventilation. Or mechanical ventilation. So again, natural ventilation, people have been living on this planet and they have used natural ventilation until the 20th century. What is natural ventilation? Fresh air enters, and if we open a window at different, then we don't need this mechanical ventilation. If we open this window here, for example, okay, so imagine that we don't have this, then we open that window, and the air goes in this direction. Perfect. Okay, so we can conditions with natural ventilation. But doing this, it means that the user, this guy, has to decide, okay, I can breathe well, I open the window, now it's healthy, so now I close the windows, and then in a few hours I will have to open the windows again. Natural ventilation works, and it's something that we have to keep in mind because it's for free. But if we need to, imagine that we can't open those windows. We are in a public building, and if you have been to public buildings, you can't open windows there. In the TDS center, if you have been to the TDS center, most of windows are not openable. And we have a mechanical ventilation system. So the air is healthy, and there are a lot of sensors and a lot of devices working well. But this is that's an example of a mechanical ventilate or a mechanical ventilated building. In most of spaces, we can't open windows in those public buildings or commercial buildings, or if you go to the cinema, you can't open a window if you are watching a movie. Okay, so all these spaces, they have mechanical ventilation. Why? Because it's impossible. If there are 1,000 people in the same building, you can't make people controlling the ventilation, because some of them, they will open a window, the other one will close the window. It depends. So we need a system, an automatic system or a mechanical system that doesn't depend on people itself. Okay, so this is the difference between natural and mechanical ventilation. We have okay, so we can have a hybrid ventilation, which is sometimes can be natural. I can open windows, but here in the toilet, I have a fan and I can extract the air here. And this is what usually happens now in our houses. We have this concept of hybrid ventilation. We have windows, and if we are living in our house, we can open the window, yep. But in mechanical supply air, we have a mechanical extraction. Okay, so I recommend you, at least I recommend you this extraction, because it will, well, it will help. Okay, so depending on the natural hybrid ventilation, I'm sure that it will work well. Okay, so there are two things. The ventilation needs, it's the concept of CFM, is cubic feet per minute. And I will show you some tables to calculate this accurately, but you have to remember this figure, 20 CFM. Okay, so for ventilation and for all the calculations, we are good in 90% of buildings. There are demanding buildings like gyms, sports facilities, or discos or whatever. So where we have a lot of people, especially moving and sweating, then this might not be enough. But for residential buildings, I think for residential buildings is 15. Okay, and the rest of the buildings is 20. But this is always the minimum. So if you apply 20 in a residential building that needs at least 15, we are good. Okay, so remember 20, because most of if we want to calculate this and you don't have the ASHRAE or any code or regulation available, you say 20 and you are not making any mistakes, because 20, unless it's a gym, a restaurant with a lot of people, movie theater, something like that, 20 is enough. So this is the CFM. CFM stands for cubic feet per minute. Okay, so this is a cubic feet per minute, and the units, we can say that this is cubic feet divided by minute. Okay, so it's cubic feet divided by minute. Sometimes you, because it's CFM, you think that it's cubic feet multiplied by minutes. No, it's divided by, it's cubic feet per minute, so it's divided by a minute. And this is it. Well, I told you that this is, it's cubic feet per minute per person. And per person, it's important. Okay. So this is cubic feet per minute per person. So we have to multiply 20 times the number of people. Okay, so if we want to start calculating the ventilation load, the first thing is 20 times number of persons, number of people. Okay, so this is the first value that we are going to need. The number of persons, so the number of people in that room. We are the architects and we can talk to the client. How many people are there in a classroom? I don't know. It depends on the number of chairs. But let's say 20, 25, 30, 15, I don't know. We have to deal with our client. Okay, we're designing a school. Okay, how many people, how many students do you want in each classroom? 20 maximum. Okay, 20 people times 20 CFM. Or how many people in the cinema? Oh, 1,000. Okay, 1,000 people times 20. Okay, so this is 20 times the number of persons or the number of people that we see them, our client, or you can decide if you are designing a single family house, how many people are there in the living room, there in a bedroom, 2 maximum. Well, there might be more. You have to. Okay, so this is that's another concept that we have to understand today. Is the concept of air leakage. So air leakage is the air that we don't want. Sometimes we can have cracks on our envelope, especially between the wall and the leakage, because this is the air that it's entering the building, but we don't want that, and we don't want it because we can't control it. Okay, it does not recognize air leakage as a valid means of ventilation. Sometimes you say, I don't have to design a mechanical ventilation because I have air leakage. Okay, if you have air leakage, it means that your building is very bad. Okay, so you cannot make up ventilation for air leakage. No, so you have to prevent air leakage from air leakage. But you will hear this. Oh no, look at this. There's a lot of air entering. So you place your hand in the window, you see, and you see the system. No, you have to fix this because this is not acceptable, and then you have to design the ventilation system. So for residential buildings, the minimum ventilation requirements, and I highlight minimum, is either 15 cubic feet per minute per person. This is what I told you before. If it's 20, it's fine. But in residential buildings, the minimum is 15. In other buildings, the minimum is 20. But if you use 20 in residential buildings, that's fine. Or we have the concept of air changes per hour. Okay, so sometimes we might find this requirement or that requirement. And we need to understand this. Air changes means that so that is the volume. So we have to change all that air. So this is one air change. Okay, so if we remove all the volume of air that we have in a room in 1 hour, that means that this is one air change per hour. If we remove this twice, we have 2 air changes per hour. If we remove only 35% of the air in 1 hour, then we have 0.35 air changes per hour. Okay, so there's a relationship between cubic feet per minute and air changes per hour. We need to know the volume of our building. For example, if this is our building, the volume is 20 something times 20 something times 30 something. Okay, so this is the volume of the building. So the volume equals, let's say that it's 20 times 20 times 30. And this is cubic feet. Okay. So if this is the volume of our building, which is 20 by 20, 400 times 30. Okay, this is 12,000 cubic feet. Okay, if we apply one air change per hour, so that means that in 1 hour, I remove 12,000 cubic feet. Okay, so what is the ventilation? The ventilation is 12,000 cubic feet. I like this cubic feet per hour. Okay, so this is the ventilation. So one air change per hour is the same in this case because the volume is 12,000 square feet. So one air change per hour is 12,000 cubic feet per hour. If we want to turn this into cubic feet per minute, then I have to cancel hours. So I know that 1 hour is 60 minutes. Okay, so if I divide 12,000 divided by 60, so this is 200 CFM. And we know that CFM is cubic feet per minute. Okay, so in this building, one air change per hour is 200 CFM. Is it clear?
Yes.
Okay, so if this building is not, let's copy this. Imagine that the volume of this building is not 20, it's 25 times 23 times 35. Okay, so now the volume is 25 times 23 times 35. It's 125 cubic feet. Okay, so then one air change per hour is this figure, 20,000 125 cubic feet. And then here, if I divide this by 60. This is 335 cubic feet per minute. Okay, so those are two different exercises. So there is not a direct relationship between cubic feet per minute or CFM and air changes per hour. It depends on the volume. With this volume, one air change per hour is 200 CFM. With this volume, one air changes per hour is 335 CFM. So it depends on the volume of the building. We can study the whole building, or we can study one of the rooms. It depends, but we need to address the volume that we are dealing with. If we are dealing with the whole building, okay. If we are dealing with just a room, okay, or just a floor, so it depends, okay. But that's the way we have to turn air changes per hour to CFM, or CFM to air changes per hour, because requirements might be in both units, okay, depending on what code you are working with, or what regulation, or depending on the state, or depending on the use of the building, you might have this requirement in cubic feet per minute, or we can have the requirement of air changes per hour. It depends on the activity, the building, where we are working, the code, the building codes, but we have to get used to working with two magnitudes here, okay? Anyway, we are going to work with CFM and cubic feet per minute. I think it's more popular, but yeah, because everybody understands CFM, and most of the regulations that I have been studying refer to CFM. But anyway, first we have to become familiar with both magnitudes. Okay, so this is the minimum ventilation requirement for residential buildings. So if you know 15, this is for, I think in the United States, yeah, I don't think there are other figures for residential buildings. But if you remember 20, it's fine, because this is the minimum ventilation requirement, so 20 is good. And with 20, you can cover 90% of the buildings that you can design. Okay, so different concepts here. First, this is the ventilation requirement, CFM and ACH. Okay, so those are two concepts that we have learned today. Two more concepts, the sensible heat and the latent heat. What's that? To understand, or very simple, it depends. And that comes from the psychrometric chart. Okay, so in this psychrometric chart, we are relating temperature and humidity. Okay, so the sensible heat is the heat related to the temperature. We increase the temperature, we increase the sensible heat. If we decrease or we reduce the temperature, so we are reducing the sensible heat. Okay, so sensible heat has to do with temperature. Okay, sensible heat, temperature. Latent heat is related to humidity. Okay, so we have both in the air. We have the temperature and we have the humidity. So when we are changing the humidity of the air, we are changing the latent heat. When we are changing the temperature, we are changing the sensible heat. So latent, it comes from Latin. Everything comes either from Latin or Greek. Okay, so what's the meaning in the Cambridge English? No. Okay, it's present, but needing particular conditions to become active or completely developed. Okay, so this is the concept of something latent. It's something that it's there, but we can't see, or we need particular conditions to realize that something is there. So this is what happens with moisture. Okay, so everything that has this word latent means that it's something that has to do with humidity, because the humidity is there. It's there, but we can't feel the humidity unless we have a lot of humidity, and then something terrible happens, and this terrible thing happening can be condensation. Or but if this doesn't happen, if we don't have condensation, we are not aware that there's a lot of humidity on our room. So this is what has to do with latent heat. Okay, so sensible heat, it's something that we can feel immediately. If the temperature rises, we feel it immediately. Or if the temperature drops, okay, we immediately can, because we are very sensitive to temperature changes. Our skin is very sensitive to that. And if we are out of this comfort range, if we are above 74, we feel, oh, it's too hot. And if we are below 68, well, it's cold here. Okay, so we're very sensitive, but with the relative humidity, we're not that sensitive. So that's why we call it latent, because it's there, it's changing, but we're not aware of that. Anyway, and now we have to differentiate between sensible heat and latent heat, and both are important. So if we have a steady number of people, if we have a few people in a room, we only have sensible heat. But when we have a lot of people in the room, latent heat can be important, because we are increasing the relative humidity, because we are breathing. And if we are in a sports facility, latent heat becomes more and more important, because we are sweating. We are literally releasing moisture or water to the air. Okay. But if we have few people, latent heat is not important, sensible heat is important. But if we have a lot of people in a room, then latent heat becomes more and more important. Okay, so that's the difference between sensible heat and latent heat. And we have these formulas. Okay, so where do these values come from? Well, it's explained here. But there is a formula to calculate the ventilation load. There are two formulas. We have to calculate the sensible load and the latent load. We didn't do that through the envelope. Through the envelope, we only have sensible heat. We don't have latent heat. We can have latent heat in the envelope, but something terrible must happen. Okay, so usually we don't have water condensing water within the envelope. We might have this, but that's something terrible, and we will feel the consequences immediately, and it will be a mess. Okay, so we assume that we don't have latent heat through the envelope, but within the room we can have latent heat, because there are people breathing and there are people releasing moisture. Okay, so here we have the CFM. I have explained what the CFM means, cubic feet per minute per person. So that would be 20 times the number of people that we have in a room. Indoor minus outdoor temperature. This is T2 minus T1. It's indoor minus outdoor temperature. And then we have this 1.1. What is this 1.1? Well, this is the specific heat of air, and it depends on the units. Okay, so it's a specific heat or a heat capacity of air under standard conditions. So we have to understand what standard conditions are. Standard conditions are like comfort conditions, conditions in which people are comfortable. Yeah, 20, let's say 60 to 70, even 60 to 80 Fahrenheit. These are standard conditions. So we have the heat capacity. Okay, so the heat capacity is the amount of heat that the air can absorb. Every single material has a heat capacity. Solids usually have more heat capacity than air. So we can store heat in solids. And we can understand that because if we apply heat to a solid element, it heats up and it starts heating up. So when it heats up, means that it's absorbing a lot of energy. Okay, so with the air, it absorbs less energy, so it heats up faster. Okay, the more the heat capacity, the less the temperature change when we apply heat. Air doesn't have a lot of heat capacity because it's very easy to heat up and to cool down. If we are heating up stone, for example, we need to apply much more energy to increase the temperature of a stone block 1 degree or 1 Fahrenheit. If we want to increase the air temperature 1 Fahrenheit, we need to apply less energy than if we're working with stone or steel or even wood. Okay, so solid elements, they have a higher heat capacity. Air and gases, they have very low heat capacity. Anyway, this 1.1 is the heat capacity in imperial units. Not imperial units, it's the units that go well with Fahrenheit and CFM, cubic feet per minute. So that's the meaning of 1.1. We're not going to explain this because it'll take hours, and just we have to remember this 1.1. If we're working with CFM, if we're working with other units, that won't be 1.1. And then for the latent load, we have to introduce the concept here of the wet bulb temperature. Okay, because this is a 0.68. Again, the 0.68 depends on the heat capacity. The heat capacity, and then we have the CFM. CFM, it's, we know that. And then we have the wet bulb temperature. The wet bulb temperature is the temperature that we feel when we are soaked, when we are covered by water. Imagine that we are going out of a swimming pool. So you are covered with water, you are soaked, and probably you will feel colder than people that are not just going out from the swimming pool. And that happens. I'm sure that you have experienced that. You have gotten out of the swimming pool, you are wet, and you say, well, it's cold. And people are lying on the grass would say, no, it's not cold, it's perfect. Okay, so this is the concept of the wet bulb temperature. Is the temperature of a thermometer that is covered with water. It doesn't mean that it's under the water. It's just surrounded by water. It's soaked, but it's not under the water. Okay, so this is the concept of the wet bulb temperature. Where can we find the wet bulb temperature? Here on this psychrometric chart. Okay, so if we enter with temperature and relative humidity, if we move in this direction, we have the wet bulb temperature here. Okay, so here, well, this is the wet bulb temperature, but we will explain this next week. So far, you only need to know that we have two different formulas. We have to calculate the sensible heat, and we have to calculate the latent heat. Okay, and here we have the dry bulb temperature, and this is the wet bulb temperature when we are calculating the latent heat. And then we have a total ventilation load. It's the sensible plus the latent load. Okay. Do you have to memorize these formulas? No, because you will have these available. But when we're dealing with ventilation loads, we need to know that one formula is not enough. We need both, and then we need to add these two, sensible and latent heat up. Okay, so now we are explaining the concept of a heat recovery. Okay, so that's another important concept that we're going to explain now. And if we have mechanical ventilation or hybrid ventilation, we have to use a heat recovery. And why do we have to use this? Well, because of the air conditions. So if it's cold, if it's winter, we can have 72 inside, 20 outside. Okay, so this air entering this room is at 20 Fahrenheit. Okay, here there will be a heating system, so we are heating up this air at 72 Fahrenheit. The problem is that we have to get rid of that air because people are doing whatever and they are releasing moisture, so we need to get rid of that air. The problem is that we are getting rid of that air at 72 Fahrenheit. Okay, well, a heat recovery is a device that can extract part of the energy from that air so that when we are introducing this fresh air, it's not at 20 Fahrenheit. It will be something in the middle between 20 and 72. So we don't have to heat up air from 20 to 72. We have to heat up air from 50 to 72. So we save energy here. Okay, so mechanical ventilation, if we use mechanical ventilation, it's recommended that we have to use a heat recovery device. And this is what we are going to see now in that video. Okay, so on that video, first we have to calculate the thermal loads, and we have two kinds of thermal loads now. Now, as of today, we will calculate, if we are analyzing buildings, we are going to calculate thermal loads through the envelope, and then we are calculating ventilation thermal loads. Okay, so through the envelope, we know how to do it. And we have roofs, walls, windows, floors, and we need the thermal insulation. And if we have a good thermal insulation, we can reduce the thermal load through the envelope. But today we're dealing with something new, which is the ventilation load. Okay, so we have thermal insulation, the wall, the roof. So all the walls, we have this thermal insulation around. We can include this thermal insulation on the floor, or if we have a basement, we know how to calculate all that. Okay, but now through the windows, oh, sorry, in this exercise, we're not going to use the windows. We're going to use the heat recovery. Okay, so now windows are not open. So imagine that we are in the TDS center and we don't have our windows open here. But we need the duct work. The problem with this mechanical ventilation and the heat recovery is that it complicates our design process because we have to create ducts and grills because we need to lead the air from some place to a different place. Okay, so this is the supply air, and then we have the return. So the supply air without this mechanical system, it would be at 20 Fahrenheit. But now with this heat recovery, we have this element here, this square, and on that square we are introducing the fresh air from outside, And this is the supply air. Then we have to return. So this is the return. And then by going through this element, this heat recovery, we are mixing the fresh air with the return air. And usually those heat recoveries are under, we can have an attic and the heat recovery can be here. But they are not exposed to the outside. They can be, but in single family houses, if we have this attic space, it's good having them there. Okay, so this is the heat recovery. So we need advice. This is a mechanical ventilation because we are moving the air. We are not opening windows here. Okay, so the windows are locked or closed. We are not opening windows. We are just dealing with this ventilation system. And indoor temperature would be at 72, and the outdoor temperature would be at recovery works. Okay, so it's always something like that. We have 4 different ducts in a heat recovery device. Through that, yep, like this. And then there's another duct going through that element. So here we can have warm and cold air, for example. And here on this element, we transfer heat. Okay, so imagine that this is cold, it's 20 Fahrenheit, and this is warm, it's 72 Fahrenheit. So in this device, we are transferring part of this heat of the air at 72 Fahrenheit, and then this supply air would be at 50 Fahrenheit. Okay, because we are transferring that heat. It doesn't mean that we are mixing the air. We are not mixing the air. So that's why heat recoveries are complicated to understand, because there is not we don't mix. So we are not transferring moisture or viruses, whatever, from the exhaust air for the return air to the fresh air. We are just transferring energy. Okay, so we can do that. And we will see what a heat recovery device is inside, but the secret is this square here, that it's mixing or is transferring heat from this return air to this supply air. Okay, so basically, the good thing here is that if this is the temperature indoors is 72, the temperature outdoors is 20, so this fresh air is at 20, this return is at 72, and this supply can be at 50, something in the middle between 72 and 20. So our heating system, we are saving energy because we are heating up air from 50 to 72. We are not heating up air from 20 to 72. So this is a hybrid system with a mechanical extraction in the natural supply. This is a full mechanical ventilation system with a heat recovery. Okay, so in public buildings, in commercial buildings, mechanical ventilation is mandatory. So we can use natural ventilation as an option because there are days in which we don't need the mechanical ventilation, but mechanical ventilation has to be there just in case. We cannot design our building just with natural ventilation. We can't do that. We need a mechanical ventilation system. And if we have a mechanical ventilation system, now it's mandatory using a heat recovery. Okay, so we cannot just supply air by mechanical means or extract this air by mechanical means. We need a heat recovery in the middle. So this is for public commercial buildings. In single family houses or in dwellings, we can use, it's accepted, we can use only natural ventilation, We can use this hybrid ventilation with mechanical extraction in natural supply. But I told you that things and codes and regulations are becoming more and more demanding. So I'm sure that even in residential buildings, mechanical ventilation with heat recovery will be mandatory in a few years. If we want to go for this passive house standard or zero energy building or whatever, it's a must. So we need heat recoveries, especially in cold countries. Okay, so probably architects working now, architects that are close to retirement with 60 or 65 or 70, they are not used to working with these heat recoveries. But you will have to work with heat recoveries by 2025. I'm sure that it will be mandatory in most Northeast codes, building codes, because you will save a lot of energy and you will increase the condition or the health conditions of the air. So both things are important. Health conditions, now it's becoming more and more important, and energy savings are also important. Okay, so here we have some schematics of this heat recovery. They are usually, but we need duct work. So you see that if we have a house with different floors and different rooms, we need ducts, and we need to supply this yellow, it's the supply air. So in each different room, we have a supply. Well, if we are working with single family houses, the supply is in the bedroom, it's in the dining room, it's in the living room, and the extract or the return duct is in the bathroom or in the kitchen. Okay, so we are designing small buildings, we are designing single family houses. So we need to find a place for the heat recovery. It's not that big. So if we have an attic or we have a basement, we can have this element. But then we have to make sure that from this heat recovery, we have a duct each different room. And I mean bedrooms and living rooms or dining rooms or whatever. And then from the bathroom and kitchen, we need the return or the extract duct here. And then we need the fresh air from outside, and then this air, it's expelled outside. Okay? But it's expelled outside after recovering the energy that this air has. So there, here we have an example of a heat recovery unit in the attic. Here we have an example of another heat recovery unit. This is in the basement. Okay, but it's always the same. We need fresh air, external fresh air. Then we need the heat recovery, and then we need to supply air to bedroom and living room, and then we need to extract air from the bathroom and from the kitchen. So it's always the same. We can, if we don't have an attic space, we can have this heat recovery on the basement. Doesn't matter. And this is a heat recovery. Okay, so this is the. So we always have 4 ducts, 1, 2, 3, 4. We have the fresh air from outside. This is the fresh air to inside. This is the supply. This is the return, and this is the exhaust to outside. And this is the device. So that cube here, that rotated cube with filters. Yeah, so this is complicated, but we don't know. We don't know. We don't have to know what's inside because we are architects. We just need to understand the heat recovery capacity, and that's it. Well, that's another explanation for this heat recovery. I like this better because there are colors and 3D. Okay, here we have an example of a problem, but I'm not going to explain this today. I will explain that on Monday. So what do you have to do now? Well, I will open an assignment and we will have to calculate this. I will provide you with data with, well, you have the dimensions and you have the volume of the building, but there are 3 different floors. So I will provide you with the occupancy of each floor, and then we have to calculate at least the CFM of each room. So you have to calculate the volume. So the volume depends on your dimensions. We have 3 floors. So that will be 30 something divided by 3. It's the height of each floor. And then the area is the area, okay? So, but there will be 3 different uses. We can have like a dwelling, or we can have a meeting room. So there will be like 3 different occupancies here for 3 different uses. And then you will have to calculate the CFM, the ventilation needs for 3 different 3 different rooms or 3 different spaces in that building. And then on Monday, I will explain you how to calculate the sensible heat, the latent heat, and how we can save energy by using the heat recovery. That will be on Monday. So what's next?